So anyway, so now I'm very happy to still be able to give the talk online. I know that my original talk title is Composite Fermions of Fractional Chain Insulators, but then I realized that there are many kinds of composite fermions, and sometimes we don't know which one is which. So I decided to change the title to better reflect our composite fermion, which is really follows the projective construction method that's being widely used in some other scenarios like spin liquid. So let me first acknowledge my collaborators. So Xiao, who is a postdoc working with me, you will realize he is only one letter different from the more famous Xiao Shi. So I want to capitalize this H here for you. And also, so Yingran is my longtime collaborator and is a professor at Boston College. Okay, so to motivate today's talk, I want to maybe begin with the question like, what is a fractional chain insulator, right? So to a experimentalist, the fractional chain insulator is very clearly defined. You basically do a Hall measurement, and if at a certain point the longitudinal resistance goes to 0, and the Hall resistance become quantized at a fractional value, then he will say, yes, I found a fractional chain insulator. But to a theorist, right, what is a fractional chain insulator? How do you know that you have found a fractional chain insulator? And so far, most of the studies really you still have to put things into a computer and do an ED calculation, and then eventually you will see energy spectrum like that with like shown here. This is a very famous threefold degenerate ground state. And if you are trying to be careful, you can also insert a flux, look at how the three ground states will evolve as you insert the flux. Even you can calculate anybody Chern number. At this point, you can say, yes, I found a fractional chain insulator. So this is really from the very early days, and many people, including Andre here, did a lot of very serious numerical work to establish the existence of the fractional chain insulator. But even with that, we still don't have a understanding like, so why would a fractional chain insulator be possible? Because right now that's just the numerical calculations or numerical experiment, right? So then since again almost 10 years ago, there has been a large effort trying to understand it, and the idea is really try to map the fractional chain insulators to fractional quantum Hall effect. So in the early days, there are Xiao and also Nicholas and Andre. They are trying to look at this one-year function representation and how can we write down a wave function similar to the laughing wave function. And then there's another idea, which is that the physics in the fractional quantum Hall effect essentially determined by the GMP algebra. So Sid, Rahul, and Sankhi, they also did this analogy. And there's a very interesting work from Murthy and Shankar that extended their Hamiltonian theory to the fractional chain insulator case. In fact, this is the route we're going to use in today's talk. And then more recently, I think the field is basically littered by the idea of ideal band, vortexal band, and color geometry, which is also kind of interesting. But if you think about it, it's really talking about a very specific condition, right? So we know that if you think about a parameter space, let's say you have some point indicated by the star here that the ideal band condition is satisfied. Okay, so we may say there is a fractional chain insulator. But if I change my parameter just a little bit, then you will say, well, since I have a gap, maybe this FCI would still be stable. But you can say, what if I change my parameter a little bit more? Well, maybe it's still there. But if I keep going, where is the boundary, right? When will we kill this fractional chain insulator? I think those are interesting questions we can think. So in general, I think you can ask the following question. The one is that we know that the understanding of the fractional quantum Hall effect really comes from the wave function. So being able to write down the wave function would be considered as some sort of level of understanding. So can we write down a FCI wave function in the same spirit as the Jens wave function that captures the fractional quantum Hall effect? And can we develop a composite fermion understanding of fractional chain insulators, right? And then, like, for instance, so what would the CF energy levels look like in FCI? And also, there's a lot of tuning one can do to a band in a non-dot level. Can we understand the phase diagram? And in fact, we can even forget about the fractional chain insulators. Can we kind of derive the Chern's wave function instead of just, hey, I have this idea, and let's write down this wave function? Is there a more systematic way to obtain this wave function? So those are the questions I'm trying to address in this talk. So maybe let's begin with the composite fermion theory developed by Chern and others. So in Chern's picture, right, the composite fermion is an electron attached by two flux quanta. So the idea is that now if you assign two flux quanta by to the electron, then the effective magnetic field felt by the composite fermion will be reduced. And in fact, we know that you can do a very quick calculation if the fitting factor happen to be P over 2ps plus 1, which is the Chern sequence. And then the resulting composite fermion will have integer fitting of P. And not only that, besides the picture, Chern also proposed that you can even write down a wave function like this. So you can see here is the composite fermion wave function, and in most cases, it's a Slater determinant. And of course, you can also assume that there's a paired state of the composite fermion or some other more exotic state. Then you attach the two flux, and here's Zi minus Zj. And in fact, to be more precise, this should be vortices rather than flux. And after that, you do a projection. So I'll give you a very quick example, right? For the Laughlin 1/3 state, we know that in a composite fermion picture, one composite fermion nano level is a complete field. So the term in red is my nu equals 1, the integer quantum Hall states of the composite fermion state. Then you attach it to flux, and in the end, you obtain this very famous Laughlin wave function. So we know that, so the idea is that when you think in terms of composite fermions, then in the Chern sequence case, the fraction quantum Hall effect are just the integer quantum Hall effect of composite fermions. And at a very special fitting of 1/2, and in that case, when the electron grab two fluxes, then the composite fermion doesn't feel any effective magnetic field, and you go back to the composite fermion liquid that's proposed by HLR. Okay, so that's sort of it's what happened if you think in terms of flux attachment. But today I'm going to introduce you a different idea that actually began with Reid a very long time ago. I guess for me personally, it really answered the question is why and how does an electron bind magnetic fluxes, right? Because when I first heard about the Chern's theory, it was very, very long time ago, it kind of baffles me, why would the electron try to grab flux? What does that mean? So in the dipole picture, you should really think about the following, is that when you what does a flux mean, right? In the fraction quantum Hall effect, if you insert a flux tube, then that will create a vortex that carries a positive charge. That is equals to nu times E, where nu is a fitting factor. So that's a very simple flux insertion argument. And because this vortex actually carries positive charge, so of course it will bind to a negatively charged electron, then this will basically form a dipole. Now, this dipole is a little different from your normal excitons because my electron and the vortex has a different charge. So therefore, the dipole is also charged, okay? So basically, I think it's a really paper back in '94. So Reid proposed the following picture, right? So you first consider a vortex. So the vortex is actually bona fide low energy excitation of the fraction quantum Hall liquid. And now if you add another additional electron, then by the Coulomb interaction, those two will bind. Then together they will form this composite object. It's a dipole, and we're going to call it our dipole composite fermions, right? And in fact, because both vortex and electrons sort of feel the B field, so their kinetic energy is quenched. So this bound state will definitely give you a lower energy. So you can imagine that maybe the ground state of the fraction quantum Hall effect can be understood as a collection of those CF dipoles. So here we can do a very, very simple calculation, is that, because my electron carries the charge minus E, And my vortex by design carries the charge of 2s times nu e, so I'm considered a 2s fold vortex. Then the composite fermion will carry this charge. And when you do the calculation, you find out that the CF dipole also has a integer filling p. So the math is in fact the same as Jen's idea, but in Jen's picture that we are changing the flux, but here we are literally changing the charge of this composite dipole object. Okay, so you can see that getting the filling factor right already tells us that this is a very promising route to go down. So let's actually take this two-particle problem more seriously. Let's consider a very simple problem, which is you consider a electron carry charge QE and a vortex carry charge QV, and they are interacting via some kind of potential, and we're going to confine this problem in the lowest Landau level. You can see that I have thrown away the mass term because when you project in the lowest Landau level, the kinetic energy is quenched. So you can solve this equation, the classical equation, very easily, and you will see that this is basically the equations, the dynamics of this two-particle system, that both will be making circles. So this is the guiding center of my electron, and this is the guiding center of my vortex. But it's a two-particle system, so in this case, you can also introduce a new coordinates, so the first one is the charge center, because QE and QV are the charges of the electron and the vortex, and you can also define a relative coordinate, so that's my eta. Now, if you plot this two-particle motion in the R and eta space, you will see that basically the charge center acting sort of like a guiding center. It's a constant motion; it doesn't change, and this relative coordinate eta acting like a cyclotron coordinate. So then you can see that the two-particle system, in fact. The two-particle problem really gave you a Landau level-like spectrum, right? So therefore, it's not surprising that if I try to solve this problem in quantum mechanics, you will see that basically I begin with a problem described by the electron and the vortex guiding center, again, because I projected into lowest Landau level. You can also rewrite this problem in terms of the center, the charge center, and the relative coordinate of the composite fermion. And if I assume that the bending potential, which of course should be a function of the relative coordinate eta, if it's quadratic in eta, then this will just give you a Landau level-like spectrum. So in this way, I return to Jen's composite fermion exactly. But again, this is a really two-particle problem, right? So let's say you can also even write down the wave function. It's given by this form here. You can see that it has a z to the m form. I'm using the symmetrical gauge, so that's the familiar wave function. But I also have I don't even know how to pronounce this Greek letter. I'm gonna call it zeta. So the zeta is the vortex of the is the coordinate of the vortex, right? So because I have a electron coordinate z and a vortex coordinate zeta here. But so far, those are just tells you the energy spectrum. How can we obtain a wave function from this? This is really very, very crucial step. Okay, so again, let's just consider this 1/3 of filling. So this would correspond to the CF filling of nu equals 1. Now, let's assume the composite fermions are non-interacting. Then the nu equals 1 CF state will be a Slater determinant given by this. So the ZIZJ is what you expected from a normal problem of electron in the Landau level. But again, I also have this vortex coordinate here, right? Now, but one of the things is that when we introduce the vortex degree of freedom, we have in fact enlarged my Hilbert space, right? If you consider an n electron system to begin with, you should have n coordinate. But I also have a vortex coordinate zeta here, which means I will have n electron coordinate and n vortex coordinate. Okay, so now you can clearly see that the Hilbert space has been enlarged. But enlarged Hilbert space is actually not a problem, and we just have to be careful and project out those unphysical degree of freedoms. How do we do this projection? Now remember that for each electron, I attach the two vortex, so therefore the vortex should behave like a boson, and they also have a filling factor of 1/2. So if you ask yourself, what is the natural state for a bunch of bosons in a magnetic field, right? But at a half filling, then the most natural one would have guessed is that it would be the bosonic Laughlin state, and in this case, it will be written just as zeta I minus zeta j squared. Okay. So in the end, we just do the projection. So the projection is, so the physical wave function will be obtained by, you begin with the Slater determinant of this composite fermion, right? Then you project out the vortex part. And this step can be very easily carried out if you switch to the Bargmann space. Then you can see that this exponential is basically delta function in the Bargmann space, and then you can obtain the Laughlin wave function. So basically, what I'm trying to show you here is that if you follow this dipole picture, not only you can get this energy spectrum right, so there is also this very simple projective construction where you can also obtain the wave function. Okay, so that's the key idea. So that's actually just to summarize that what we are doing. I know that there's a lot of information that has been dumped here. So basically, we begin with a Hilbert space of the physical electrons. So those are the red dots here. So those are the electrons living on the inside the lowest non-dot level. And what we did is that we then introduce a fictitious degree of freedom, which we call them vortices. So the vortices will live in their own lowest non-dot level because they carry different charge decided by the electron filling factor, right? But then in this enlarged Hilbert space, the electron and the vortex, they will bind to form a composite fermion, and in that case, the composite fermion state can be written as some Slater determinant, which means that you can actually perform Hartree-Fock calculation in this enlarged Hilbert space. Now, once you finish the calculation, you will obtain a Slater determinant of the composite fermion. Then in the end, you need to do a projection, which we assume that you have to use this nu equals half Laughlin state. So I have two comments to make. If you follow the exactly same procedure for non-dot levels, they obtain the physical wave function will have the exactly same form as the Jens wave function. So just as a justification of this idea really work. And secondly, I would like to mention that in addition to electrons in the non-dot level, you can also consider bosons in the non-dot level. And in the bosonic case, this idea is actually way better established because in that case, you attach a single vortex to a boson to form a composite fermion. So the vortex filling will be 1, and they happen to behave like a fermions. So the many-body Hilbert space will be exactly 1. So in that case, you don't have to guess what kind of vortex state it is. It's just the nu equals 1 Laughlin state, or nu equals 1 the integer non-dot level state. Okay. So those are basically the rough idea. So now the question is that how can we make this into a quantitative theory? So this is what we have recently figured out. So let me just give you a very quick rundown of the basic procedure. So it's kind of a little bit more technical, but the recipe is very clearly spelled out. So we begin with a band projected Hamiltonian, right? You have your band dispersion, and then you have your interaction that's written in terms of the normal ordered interaction term, and this rho bar is the projected electron density operator. So we are assuming that the interaction is the density type. Okay, so basically standard Coulomb interaction. Okay, that's our starting point. Then the next step, as I mentioned earlier, we are going to enlarge the Hilbert space by introducing vortices that carries a fractional charge. So this is by design, which is given by 2s times nu e. Okay, so in fact, if you think about a fractional changelators, talking about a vortex doesn't make much sense. So they are not like a real vortex as in a non-dot level case. You can just assume there are some kind of fictitious particles, but they carry the charge given by this guy here. Okay, and in addition, they will also feel a uniform magnetic field that's set by the electron Chern number. So the B field will be, effective B field will be given by H divided by E, and then by the unit cell area of the electrons. Okay, so basically we assume that the vortex will have a constant barrier curvature if you switch from the real space to momentum space. Now, a very, very important fact is that since the vortex is fractionally charged, so if you think about it, now we are putting the vortex on a torus, you can think about the magnetic unit cell, then it's a 2ps plus 1 times the electron unit cell, right? I'm still assuming that my filling factor is P over 2ps plus 1 in the Chern sequence. Okay, so so now we have enlarged our Hilbert space. So now I have electrons and vortices in my system. Then how do I bind them together? So the binding is basically achieved by the following procedure. And so we have the electron density operator, right? But now I have two types of charge in my system, electron and the vortices. So in that case, so the actual charge density, you would write it as rho bar, like basically the electron density minus the vortex density. Okay, so the C square here basically is means the vortex charge. So those are the sort of charge density you would have written down if we are dealing with two types of different charges. Okay, so because we have already assumed the vortex lives in its own Landau level, so then the vortex density operator is basically given by those GMP operators, where R is the guiding center of the vortex. Okay, so this is called the preferred charge substitution. Now, this is a very, very detailed, but it's an important technical step. Is that recall that the interaction here is actually normal ordered, right? This is my electron density operator. So when you replace the electron density operator with the preferred charge density operator, you need to unpack this normal order first. Then you can do this substitution, and then eventually you will obtain a CF Hamiltonian that's given by a single particle part plus the interaction part. Well, the interaction part are just the standard normal ordered interaction, but in terms of the preferred charge density operator. Then the single particle part, the H naught, is given by this guy here. You can see that first there's the band dispersion will be there. That's not a surprise. But then this term is really come from the normal order and then renormal order procedure. So it will give you a term like that. Okay. So before we dive into details, let's just get one fact straight. You can see that this Hamiltonian in total, it describes a periodic system, right? But what's the period of the system? Now, again, if you assume that the electron filling factor is in the Chern sequence, then as a composite particle, the composite fermion period must be compatible with both the electron and the vortices. Since we mentioned before that the unit cell of the vortices, or the magnetic unit cell of the vortices, will be 2ps plus 1 log times the electron unit cell. So the composite fermion period is also 2ps plus 1, which means that then for the filling factor of the composite fermion band, you will have an integer filling. So you can see that this is really parallels what we already know, or what we kind of anticipate, right? So the fractional translator of electrons can be understood as the integer translator of composite fermions. Okay, but the Hamiltonian in this form is already can be calculated, but it's kind of very opaque. Let's just look at a small q expansion, then we can sort of flash out what's the physics in there. So basically, when you have this density operator in a small q expansion, we're gonna expand to the second order in q. Then the single particle CF Hamiltonian takes this form. I will explain this to you one by one. So when you look at this single particle Hamiltonian, so the first is to see there's a effective mass. The effective mass is entirely driven by the interaction. again, like if this is something that kind of expected, right? In fact, I think one of the criticism of the HLR theory is that, so in this singular gauge transformation, the bare electron mass enter into the theory. But you can see that because we build our theory entirely from the lowest non-dot level, there's no bare electron mass. The CF mass is entirely coming from interaction and given by this expression here. Now, the next one is you can see this is a so-called trace condition. So because I'm using the convention that the Chern number is -1, so this really should be written as a trace G minus the absolute value of the Barry curvature. So that's very interesting because I didn't set out to look for trace condition. It just naturally emerged in the small q limit. And finally, let's look at the third term. This operator D here is basically the covariant derivative, right? Now we know it's the projected electron position operator in a band. And the Z here is the projected vortex coordinate. So the last term has a very simple physical meaning. So this is the projected electron coordinate. This is the projected vortex coordinate. So this basically tells you that this is the relative interaction between the electron and the vortex. And in the small q limit, they adopt a quadratic term. It's basically electron position minus the vortex position then squared. Okay. So this is the sort of meaning of the single particle composite fermion Hamiltonian. All right. So let me just keep commenting on this equation because this is really very, very nice looking equation. So now you look at this, right? You see that this is basically like a k-space half-state butterfly problem, right? If you just replace K with R, then this is basically solving some kind of problem of a particle moving in a periodic scalar potential with a periodic magnetic field. So the first two terms, this band dispersion plus the trace condition are just the scalar potential, right? And the D, remember D is the covariant derivative is IDDK plus the Barry connection. So then this term in blue represents a periodic magnetic field. And in fact, I already written this term using the complex notation. So this is basically the Aharolov-Kasher Hamiltonian. Okay, so now with this understanding, you can finally understand what exactly those people are saying about the trace condition. Because in this single particle CF Hamiltonian, when you set the band dispersion to be 0, and you assume the trace condition is satisfied, then the CF Hamiltonian will only have the last term there. And because the last term is the AC Hamiltonian, then we know that the energy spectrum, the lowest band will be flat. And but the second band, the third band, they can have some fluctuations. They can have dispersions. Okay, so which means that even if the trace condition is not satisfied, but you have a band dispersion there, you can compensate the trace condition. So people say, oh, you really want to make your band flat, but you can see that if the trace condition doesn't hold, then there's a possibility that if you made a band a little bit dispersive, it could help to stabilize the fractional insulators. And secondly is that, again, even if the trace condition is satisfied and the band dispersion is 0, but this kind of AC Hamiltonian only guarantee the flatness of the lowest band. So if we are talking about Gen sequence that's not a Laflin state, say 2/5 or 3/7, and in that case, we are occupying more than one CF band, then the trace condition is basically have no predictive power there. Okay. So in the following, what I'm going to do is that I will ignore the CF interaction term and just focus on the single particle CF Hamiltonian. We're going to solve it and see how it goes. You will see that even without considering the CF interaction, we already captured a lot of physics. Okay, so now let me apply our theory to the twisted MOT2 bilayer. So this is my Hamiltonian, right? Again, those are the so-called periodic potential part, scalar potential part. This is the vector potential part. Okay, And this is sort of the continuum Hamiltonian of the MOT2. I'm sure you guys have heard about this many times in this workshop. So I want to show you this figure. What this shows that is this x-axis is the twisting angle. So theta went from 3 to 5-ish. And then those curves tell you the different terms in the Hamiltonian. Now you can see this blue curve is the fluctuation of the barrier curvature. So around the 3.5, the fluctuation of barrier curvature is lowest. If you increase the twist angle, the fluctuation becomes big. And then you can also look at the twist condition. So the twist condition, in fact, are pretty good. They are, as you increase the twist angle, it will increase, but not by a lot. So would say in this whole range, the twist condition is almost satisfied. And now look at this red curve. The red curve is the sum of the first and the second term. But you can see the red curve, in fact, because when you increase the twist angle, the band dispersion becomes really, really big. So then it will increase drastically. So that's how the terms in the Hamiltonian in this HCF Hamiltonian changes. So now given this, you would so let's actually look at the band structure at a 3.5 degree, where you can see that all the terms are kind of small. And in comparison, we're also going to look at the CF band structure around here when the periodic potential part becomes really large. Okay, so here is the calculated CF band. So because I'm considering 1/3 of filling, so only the lowest CF band is filled. So this band is filled, and then this band is empty. That's the first band, that's the lowest band, that's the second band. You can see that they are really flat, right? So this kind of mimicking what you would expect for the lambda levels of composite fermions. So that's at a 3.5 degree when everything is flat. Now, if I go to 4.25 degree, that's when the twist condition roughly holds, but the barrier curvature fluctuates a lot. Then now you see that the lowest band are still kind of flat because, but for the second band, then the composite fermion band becomes very, very highly fluctuate, right? So now if you think about the band gap here, so then this will have a larger band gap from here to here. But then this one, because of the fluctuation, the band gap will be reduced. So in other words, that the composite, the fractional change later is marching towards its death. Okay, so now what we can do is that, now remember that because we are talking about the composite fermions, so this gap, if you ignore the composite fermion interactions, then this gap is roughly the activation gap, right? So we can plot this gap as a function of the twist angle under the dielectric constant. So the dielectric constant basically is tuning the strength of the Coulomb interaction. If I go to a larger number here, I'm basically weakening the interaction. So you can see that this is my CF phase diagram obtained by solving this single particle CF Hamiltonian. It tells you that as expected, right, at 3.5, when everything is flat, you have the largest CF gap. But then as you increase the twisting angle, or if you decrease your interaction, then the gap will decrease and the whole system will be killed. Okay, so again, I want to remind you that this is really one-shot calculation. We didn't even do Hartree-Fock, just a single particle CF Hamiltonian. And this is the same calculation, but this is the calculation using numerical, the ED calculation, but it's actually for the same Hamiltonian. And what's plotted here is the many-body gap. So if you compare those two, you can see that this very simple mean field level calculation can really capture a lot of features in the ED. Like for instance, the many-body CF gap is the largest at 3.5, and also here, yeah, I mean it's the same color, but if you plot 9 card, you will see the highest value of the CF gap is also roughly here. And as you increase the theta, then the FCF will be destroyed. And here the same. If you increase the theta, the CF gap will start decreasing. And then very interestingly, right here, you can see from ED calculation, if you decrease your energy, you will kill the fractional change related state. And then here is the same. You decrease, if you decrease your interaction, the CF state will be destroyed. Why is this interesting? Because if I'm only tuning the interaction strength, then I'm not touching any of the band geometry, right? So therefore, you would argue, hey, look, I have ideal band condition realized here, so I will always have FCI state. But our calculation says no, the interaction actually matters, pretty important. So how does the interaction enter into this picture? So let me show you this whole picture here. Again, this is a CF band here, right? Now let's decrease our interaction, see what's going to happen. If you decrease your interaction, let's say at 35 for the direct constant, that's a CF band. First you can see that all the bands are plotted using the same scale. So you can see that these unoccupied bands now come down quite a lot. And this is expected because if you think about lambda levels in the composite fermion picture, the level spacing is basically determined by the interaction strength. If I decrease my interaction, my level spacing should become small. However, the difference is that I actually have some dispersion in my system because even though everything is kind of flat, but they are not exactly flat. So therefore, when you reach a certain critical value of the interaction strength, then the top band and the lower band, they will touch each other. Therefore, they will kill the FCI. But if you just think about the non-down level case, and if we ignore the non-down level mixing, right, the gap will never be closed. It just keep increasing, or it just keep decreasing, and when interaction go to zero, the gap will close. But here, there's a finite interaction strength, a critical value. Below that value, the FCI will be killed. All right. So now this just shows you the energetics of the composite fermion picture. Now we see the CF band gap can be used as a very good indication to indicate whether the FCI should survive or not. But what about the wave functions, right? Can we write down a wave function? Well, it's actually very simple to write down the wave function. Why? Because we have already solved this problem. We have a CF band, and so we can form a Slater determinant. As I said earlier, we're going to continue to assume that the vortex is the 1/2 bosonic Laughlin state. Okay, so you do a projection. Now you can see that this is the overlap between my projective constructed wave function and the ED wave function. So again, this x-axis is a twisting angle, and this is the overlap. You can see at 3.5, that's when the system behave most like a non-down level. I have very high overlap. It's 99%. If you increase the twist angle, you can see that the overlap holds relatively well, right? And even after at the ED level, the FCI is destroyed, but I can continue to trace those many-body eigenstates at the original 3 momenta. You can see the overlap are still pretty good. Okay, so again, I don't have an analytical form for the wave function, but I do have a numerical way to write down the wave function that's really in excellent agreement with the ED calculations. Now, finally, what about topology, right? I showed you the energy spectrum, I showed you the wave function, but what's interesting about the fractional change related state is the topology. So we have just figured out this actually last week, that in this kind of projective construction, we actually have the many-body number of the electron equals to the many-body number of the vortex times the many-body number of the composite fermion and divided by their difference. Okay, and in our construction, because we have always fixed the vortex to be the 1/2 bosonic Laughlin state, so the many-body number of the vortex is basically -1/2. The minus because the vortex has opposite charge as the electrons. So in that case, the Chern number of the electron equals to this, and you can see this is essentially just the Chern sequence. Okay. All right. So with that being said, let me give a summary. So we have developed a projective construction of the composite fermions in a partially filled Chern band with C equals 1. We show that the wave function has a very high overlap with ED, And also the preferred charge give you a very accurate and very, very quick way to actually, calculate the phase diagram. It really take you 5 minutes on your laptop. So the basic idea is really the same, is that, I have my electrons live in a block band. So I made this a little bit dispersive, so that's a band. But then I introduce a fictitious vortex degree, which is lives in its own lambda levels. And then you can solve the composite fermion problem in a enlarged Hilbert space. But finally, you need to project back to the physical space. Okay. All right. So let me just have one more slide to talk about some outlooks. So far, I would say that we have developed a machinery, and if I'm being a little bit boastful, I would say it's a very powerful machinery. But the physics we uncovered are kind of some known or expected physics. So basically in MOTU2, all the FCI state should be adiabatic connected to the quantum Hall state. But what if I have a band inversion in my composite fermion state, right? Say now my composite fermion carries number 1 for a single band. What if it carries number 2? Then in that case, you are going to have a new state. You're going to go away from the gen sequence. So those are some things really interesting, and we are working on it now. Then the other things that we have ignored the CF-CF interaction. So of course we can include it. Then you should be able to calculate the magnetotons, or even some more exotic state like CDW state of CFs or paired state of CFs. And in terms of the actual formalism, and one of the sort of shortcomings is that the vortex state is fixed to be the bosonic Laughlin state. The reason is that if we go away from it, right now we don't know how to do it. But you would imagine that if my electron can feel the lattice effect, the vortices should also be able to feel it. So in some case, at least the vortex should be a bosonic FCI state rather than just the standard 1/2 bosonic Laughlin state, right? So I think that's actually a lot of optimization one can do to make this theory even more quantitatively accurate. And you can even think about some other very interesting scenarios, like because my vortex are bosons, so what if there's a Bose condensation in my vortex state? What does this signal in my electron space? So definitely it should be a quantum phase transition, but what kind of phase transition is that? We don't know yet, but I would say right now we develop a tool, but we really haven't uncovered like how powerful it can be or what kind of physical result we can get. Okay, so with that being said, I want to just thank you for your patience, and please ask me questions.
Thank you very much, Lee. Questions?
Very, very beautiful. Just kind of remarkable. So I have a couple of questions. So first, your Hamiltonian, when you take the expansion, that's a small q expansion, right?
Yeah.
To get the quantum geometry.
Yeah.
But normally you have g vectors, right? You have plane waves. That introduces extra terms, or that doesn't matter?
It doesn't matter because here everything is done in a block basis, so I didn't even wave expansion. Yeah,
I see. And then so let's start with the Hamiltonian that's flat band, so it's projected, right? So epsilon of k is 0.
Yeah.
Right. In that case,
yes.
So right, you made this point that I can change. I can go away from the ideal condition and cancel the kinetic energy.
Right.
So I can have FCIs with some kinetic energy. But if I start with 0 kinetic energy, then is it true that the best FCI is at the ideal condition, or do I have a right? This is basically 0 shot, as you said, or do I have self energy effects in the interacting term? That will, can I get rid of?
So Andre, I don't think I have fully understand the consequence of the Hamiltonian that we are staring at right now. We have done a lot of sort of very simple, just numerically calculate band structure that we can do, right? It seems that without considering interaction, if the trace condition is satisfied, the gap is always the largest, but I will not say this is always true, because I mean right now I write down the Hamiltonian, I can solve it, but we really don't understand a lot of it, like how do you even get band inversion? What kind of parameter regime give you the desired properties? So yeah, I don't have an answer for you, but I would say in our limited numerical experience, it seems that's the case.
Because I would say if let's say we can make epsilon of k 0 by hand by projection to start off with, then yeah, I would say that you still can't get away from, it'll go into the form factors of the interaction, and then it should still be that the trace condition will be violated still for the best FCI. If I start off with my band should know somehow initial epsilon of k non-zero. Even if I make it 0 by hand, by projection.
Yeah, but those would be small, because all the band structure I showed you, right? Those are not obtained from the small q. Those are obtained from the full Hamiltonian without doing the small q expansion.
I see.
But the small q expansion just to try to squeeze out this trace condition. Right. But we do have a method to just do the calculation without even care about what trace condition is.
I see. Thanks.
Is there a way to probe the vortex, the state in which the vortices are from your ED directly?
Okay. That's a very, very good question. That's actually exactly one of the route we are thinking, right? So basically, you can ask yourself this question, because we motivated this idea of vortex by saying that the vortex can be understood as generated by inserting a flux. It's basically it's excitation, right? Then you can ask yourself, if I treat this vortex as a particle, say it has a location eta, what's the dynamics of eta? Then you can do a standard time-dependent Lagrangian calculation, and the calculation will be the same as what Wilczek and when they proved the fractional statistics. You will see that the vortex will feel a effective uniform magnetic field. Now, switch to the FCI, you can still insert a flux to generate a excitation. That's no problem. Then you can ask yourself, what is the effective dynamics of that excitation? Then it will. We don't know how to do it, but you can sort of see it will be a vortex moving in a non-uniform magnetic field with the period of the magnetic of the lattice structure, or the vortex will feel a non-uniform Barry curvature, right? So what I'm thinking right now is that if I already have if I can do ED, I can then really generate a vortex, a real vortex, which is basically a whole excitation. Then if there's a way I can massage out of effective dynamics or effective quantum mechanical description of the vortex, so that would help us to further massage the vortex into a better variational ansatz than just right now the plain old Lafanian state.
Thank you.
More questions? Okay.
Is there a characteristic distance between the vortex and the charge which can be probed by finite Q measurements?
Yes.
So what is it? Basically the size of the dipole moment.
Yeah, I know, Adi, I know exactly what you're asking, and I expect this question from you, but we just haven't looked at the distance yet. But since I have the Slater determinants, right, I can I can basically calculate the expecting value of my dipole moment in that state. We just haven't done it yet. But I would say that, for instance, this same dipole picture you can apply it to the CFL, and in the non-down level case, we basically can recover almost all the result.
Yeah, in the Landau level case, it recovers the results of HLR, basically the dipole picture.
Yeah.
Right. So the only length scale that appears in the response is the cyclotron radius of the composite fermions. I wonder if here there's another length scale that shows up.
The ninth scale itself, I think it's the same, right? Because basically, it's the unit cell length of the electron. That's basically the cyclotron or the magnetic length in the non-down level case. But I think the difference is because I have a case-based dispersion or dependency. You can just think about the size of an exciton in a semiconductor, so it will depend on the center of mass of that exciton. So in this case, we should have similar physics there.
Question?
So if I look at the Landau level problem, coming back to actually Oscar's question, if I look at the Landau level problem and look at the Haldane pseudopotential for 1/3, is there something in the spectrum that would tell me what state my vortices are? I would have to look at the spectrum with -1 particle, or what exactly should I do? Just for the pseudopotential, for the ideal.
Yeah. I think at this point the vortex state is really put in hand by hands, right? So you could ask what is the actual. Okay, so you can think about a variational procedure in the following way: that given a vortex wave function, I can construct my composite fermions, I can do my calculation, then I can project it back to the real physical space, then I can calculate the total energy of the system. So if you vary that vortex state, eventually, you will find what is the true vortex state one should use. But of course, this procedure is impossible. You are talking about a huge Hilbert space. So I think that's sort of the only weak link in the theory, that we have to put a vortex state by hand. However, again, if you go to this bosonic case, in there you attach, let's say if you have a for the bosonic case, you have a fitting factor. It actually doesn't matter what kind of fitting factor. If you attach one vortex to a boson to form a composite fermion, in that case, the fitting factor of the vortex will be 1, but they are fermions, right? So then the many-body Hilbert space will be, the dimension of the many-body Hilbert space of the vortex will be 1. In that case, we don't have to guess what kind of vortex state it is, because that's only one state. But once you attach more than one vortex to the particles, whether it's boson or fermions, we are going to run into this problem.
Okay, thanks.
Okay, thank you very much, Lee. And with this, we close this session. We go for lunch.